Hello. Suppose I have a state A which is a linear superposition of many state A1 to AI. Okay. Now I have told about superposition of states, and there I told that when I make a measurement of this kind of state, I do not get average values. Okay, like if A1 corresponds to A1 and A2 corresponds to A2 or AI corresponds to AI. Okay, when I make a measurement on A, I do not get average of these values like classical mechanics. What I get is that I get any of these values. Okay, any of these values. Suppose I get AI. Okay, now if I get AI, okay, so and again if I make another measurement, what I mean to say is that I make a measurement, suppose alpha, okay, on A. This is operator and this represents dynamical variables or observation. So when I make an observation alpha on A, this gives me a value AI. Suppose, okay, now if I make another measurement, okay, if I make another measurement on this case, I get same value AI. This is experimental fact. Okay, so I mean to say is that suppose I have a coin, okay, and I have a coin and it has head and tail, and I toss it and I get head. Okay, now if I want to look at the coin again, I see this head again and again. So when I have made a measurement, okay, now I mean to say that when I made the measurement, I get AI, and when I again make a measurement, I get AI again. So it is like this whole state collapses to a state, the state which corresponds this AI. Now what is the state corresponding to this eigenvalue? It is AI. Okay, so when I make a measurement on this state, it collapses to a state AI. Okay, so this is the collapse of states. It may collapse in any states. It may collapse to A1 or A2 or any kind of states. Okay, now when it collapses to a state, okay, and when I make another measurement, we get the same result. Okay, so this is like a collapse. So alpha is a operator, and the eigenvalues or eigenstates of this alpha are these eigenstates. Okay, so if A1, A2, AI are the eigenvectors for this alpha, we can make any arbitrary vector from these states. Okay, so this is like an arbitrary state. Okay, and this arbitrary state is a linear composition of the all possible eigenvectors of alpha, and all possible eigenvalues are these. So when I make a measurement on this, I will get any of these eigenvalues. Okay, so this is summation. Okay, and the summation is over all kind of eigenvalues. Now we can change the summation to integration for continuous case, like we can say that the summation here, that there is summation here. So here we change summation to integration. Okay, so this is integration over this text AI for different values of eigenvectors. Okay, as this is a continuous case, our eigenvalues will not be discrete. Our eigenvalues will be continuous. So the integration will be over dai. Okay. So for all the values of AI, suppose the lower limit of the eigenvalue is A0. Okay, and the upper limit is An. So the eigenvalues may be between A0 to An. The eigenvalues can be any number between these, and it is continuous. So any arbitrary state will be integration over all the possible eigenvalues for every eigen values. Okay, so this is the definition. Now suppose now I'm going to derive an equation for dynamical variables. We have all kind of operators. Okay, now we have to make sure that this operator represents a certain dynamical variable. Okay, now what will be the equation which will determine that this operator is really a dynamical variable? Suppose C is like operator, okay, and it acts on a k vector P, okay, and this k vector is a linear supercomposition of all the eigenvectors corresponding to this operator. Okay, so the eigenvectors are suppose Ci, okay, Ci and capital Ci. Okay, so this is a superposition. Now the values, now the operator will give me a certain eigenvalues for certain eigenvector. So the eigenvectors are okay. So these are the eigenvalues which corresponds to this operator, and the corresponding eigenvectors for these eigenvalues are C1, C2, C3, Ci. Okay, so now suppose this is an operator, these are product. Okay, so what will be the value of this? Suppose take this product and operate this on this, that P. Now what will I get? Now P, now when I operate P, when I operate C on this P, it may give any eigenvector. Okay, suppose eigenvector is not this one, another this one. Okay, so when I operate this on this, it gives me this. Okay, now this eigenvector obviously correspond to a eigenvector here in the summation. So there is a product correspond to this in this multiplication, that is this one. Okay. And when this acts on this P, it will give me what? Well, if this is I and this is I, then it will obviously give me 0. And when a product is 0, the whole multiplication will be 0. Okay, so for any kind of values of P, it obviously gives me any of these eigenvectors, eigenvalues. So whenever it gives me a eigenvalue, it will be nullified by this C minus Ci. Okay, so when this equation holds, we can say that this is really a dynamical variables. Okay, now for a non-zero value of this one, we can say that this is itself 0. Okay, so it is 0 for a non-zero state. So this is the equation which tells me that operator is a dynamical variable and which is not. So this is the condition. Okay. So I have told about bra and Kate's vector and linear operators. Okay. Now bra and Kate's are like vectors, and obviously these vectors follow an algebra, and these bra and Kate's are vectors which lives in a vector space. Okay. So bra and Kate's are the vectors which corresponds to states of the system, and these vectors lives in a particular vector space, and in that vector space the length of every bra or every Kate is finite. Okay, or the scalar product between bras and Kates are also finite. So this kind of vector space is called as Hilbert space. Okay, so the bra and Kate which correspond to state of physical system lives in Hilbert space. Okay. The condition here is that the length of every bra should be finite and the scalar product should also be finite. Okay, and we have discussed about this all in the properties of the bras and Kates which corresponds to state. So these bra and Kates lives in Hilbert space. Okay. Hilbert was a mathematician of Germany, and now the physical significance. Now I have told about the physical significance of states, physical significance of operators, and many relations between them. Now there is another physical importance which I have not told. Now before going into that physical importance, let me show you something. Okay, suppose I have a observable. Suppose this is a observable, and in classical mechanics, what happens in classical mechanics, I have a definite value for every dynamical. Okay, momentum or position, every physical quantities or every dynamical quantities. Here is a linear operator. For classical mechanics, we have a definite value. Now, what will be that kind of value in quantum mechanics? Okay, which will be analog to classical mechanics. Now, you may say that this is a number. So this number can be analogous. This number can be analogous to that classical mechanical number, because this corresponds to a operator, and for fixed operator I have a fixed number. So this can be that number that we have in classical mechanics. But there is a problem. There's a problem is that this number is for two different states. But in classical mechanics, for a fixed observable, we have a fixed number for a fixed state, one state. But here this number is for two states, x and y. And there's another problem is that this may be imaginary number. This may not be always real number. Okay, and another problem is that we cannot always normalize this, because x is a different state, y is a different state. Okay, and we have scalar product those two states, so we cannot simultaneously normalize this thing. These three problems can be eliminated if we say that x is y. Okay, so this number becomes what? This number becomes this. This number is for a particular state which is x. This number is for a particular dynamical variable which is she. Okay, now this number is also real. This is real number I have told about before. Okay, this is real number, and if I multiply x with a number, suppose IC, if I multiply this number with x, it will not change. because this is a branch escape, it will cancel because this is a complex conjugate of this k. Okay, so this number can be that classical mechanical number, but there is a slight problem here. Now I am trying to say that I am trying to find a classical mechanical or a classical analog to this number. This is a number which is a quantum, which corresponds to a quantum mechanics. This is not classical mechanics. We are not doing classical mechanics. This is a quantum mechanical number. Okay. Now I am trying to find that as this is a number, this number corresponds to any classical number. Okay. Like eigenvalues are the numbers which correspond to the results of measurement. Okay, so this is also a number. So we were trying to find out what is the physical significance of this number. This is the point of me doing this. Okay, so what is the problem? Problem is that suppose I have two observables. These are two observables. Okay, now in classical mechanics, if this gives me a number, suppose this, okay, and this gives me a number n1. Okay, now if I sum this, the corresponding value will be the summation of this state in classical mechanics. Okay, so if this is a number, it should follow this. Now what will be the case here? If I have a number operator this, and if this is the number, sorry, then this must be that this must be the case if we try to find the physical significance of this number. So this must be true, and we see that it is obviously true. The algebra that states follow, the algebra the operator follow, it is true. So this is not the problem. So summation of this number for different operator is also summation of the is also equal to the summation of the operators. Okay. So this is true, but if I multiply this, if multiply this operator with this operator, will be this multiplied to, in classical mechanics it is true. Okay, if I multiply the operator, the corresponding number will also be multiplied in classical mechanics. But here it is not so. Here it is not equal. Okay. So what can be the physical significance of this number, which follows the summation but does not follow this kind of multiplication? The answer is, it is like the average of measurement. Okay. If I make two different measurement, okay, and if I sum these two measurement, the average will also be summed. Like suppose I have 10 boys here and I have 10 girls here. Okay, and the average of age is suppose 17, the average of age is suppose 18. Okay, now if I add these two measurements, the total kids will be 20 and average will also be multiplied. Average will also be summed. So average follows that summation, that property. Okay, but if I multiply this, the total kids will be what? 100. And the average of 100 kids won't be the multiplication of these two separate average. So average clearly follow these two. So this is the physical significance of this number is average. Average of what? Average of different results corresponding to this operator. So this is the physical significance. Okay. So let me make the conclusion here that this is a operator, okay, and this operator gives different kind of results in different type of measurements of this particular dynamical variables, okay, because this has different eigenvalues of a1 to dot dot an, and the result could be any number, okay, and if I average these numbers, the average will be this for a particular state x. So this is the physical significance. This is average of results. Okay. Now, suppose I have a operator this, and there is a function of operator which is this. Okay. Now let me define this function. The definition of this function is that when this operator gives me the result A, particular result A, this is 1. But if this particular result do not give me A, then the operator is 0. Okay. So the definition is that this is like a omega delta. When the eigenvalue of this operator is A, it is 0. And when the eigenvalue of this is not A, this is 0. Now, does it ring your mind? This is like a what? This is like a probability. Right? If I have a measurement and I want to find the probability of A, if I don't get this result, the probability will be 0. But if I get the result A, the probability will be 1. Right? Okay. So this is like a probability. You can say this is a probability operator. Now, what will be the probability here? Obviously, this is not a probability because this is an operator. Probability is a number. Okay. So what will be the probability here? The probability is defined as this. This is the probability. For a particular state X, for a particular observable C, the probability of getting A will be this. Okay. Now this is a definite value of A. If I have a range, if the eigenvalues are continuous, suppose, then A to A plus B. What is the probability that the eigenvector will lie in this range? Okay, so we have to redefine this function. We have to say that this is 1 when the eigenvalue of this C is A to A plus G. This is 0 when this is the eigenvector not this in this range. So we have to redefine this function, and the probability will be this, and it will be denoted as PA dA. Right? If I increase this, the probability will increase. The probability of the eigenvalue lying inside this range will increase because I am increasing this dA. So this will be multiplied with this probability. Okay. So this is the physical significance of this is the probability. Okay. Now suppose X is the state. Okay. And this is superposition of 3 states. Okay. C1, this state gives me suppose A1, this state gives me A2, this state gives me A3 for a physical quantity or operator, say alpha. Okay, so when alpha operates on this, it gives me sometimes this, sometimes this, sometimes this. Okay, the results are between these 3 values. What will be the probability that I get A1? What will be the probability that I get A2? What will be the probability that I get A3? we can derive the probability from this definition. Okay, so let me use this definition. Now this is the operator, so operating on this state. Now when I operate this operator on this operator when operates on, suppose here A1. Okay, I am trying to find the probability of A1. Okay, now when the eigenvalue of this is A1, it will give me 1. So when this operator on this thing, it will obviously give me C1 into X1. Okay, because the eigenvalue of this operator is 1 for when this gives me A1, but this does not give me A1, this gives me A2. So when this operator on this, it will give me 0. Similarly, it is A3, so when this operator on this, it will obviously give me 0. Okay, so when this thing operates on this, it gives me what? It gives me C1 and X1. And C1 is a number. Now what is this? I am scalar producting this bra with the get this. And this is a get. Now we have to complex conjugate the whole thing to get the bra. Okay, so we are complex conjugating this. So this will become this. It will complex conjugate. This get will become bra. This will complex conjugate. This will be X2. This is complex conjugate, and this is X3. And when I product this one with this, okay, these are all orthogonal states. When this scalar product with this, it will give me certainly 1 and multiplied with this, so it will give me C1 star. But when I scalar product this X1 with this, it will give me 0 because this X2 and X1 different states and these are orthogonal, so this is 0 and this is also 0. Okay, so this one is C1 multiplied by C star. So this is known, right? I told in the previous first videos that when I try to find the probability of particular result, I get the coefficient square. Now our new definition gives me exactly this result. So in that video I have told that I will prove this. I proved that probability is indeed this one. Now I have proved it. Our mathematical formulation proves that this is indeed the probability, and this follows the experimental fact. So our mathematical formulation is concrete. It has no loopholes because it gives me same kind of result that we expect in experimental facts. So our mathematical formulation have concrete, and we have done mathematical formulating the quantum mechanics, the bras, the K's, the operators, and the physical significance of these things, and the physical significance of the equations. And the equation will give me certain experimental facts like this. Okay, so that's it. Mathematical formulation of quantum mechanics.